So folks, in this problem we're asked to evaluate a given line integral, but we're asked to do so not directly, but by using Stokes' theorem. So our curve C, which is what we're taking the line integral around, is the intersection of these two surfaces right here, and we're told that C is oriented counterclockwise. So it may be a little bit hard to see that this is a circulation integral given this format. I prefer to write them this way. So if I rewrote this as y, z, x for those three component functions, and then I dotted that with the parameterization of our curve C there, any parameterization of our curve C, then this should now look like a circulation integral. And we could try to evaluate this circulation integral directly by coming up with the parameterization of C, but instead we were asked to use Stokes' theorem on this. So remember that Stokes' theorem says rather than evaluating the circulation around the boundary of a surface, we could go ahead and calculate the flux across the surface. So at every point on the surface, we're going to calculate the curl of the vector field at that point, and we're going to dot that with the normal vector of our surface and ask how much are they in alignment. We're going to sum those up over all points in our surface, and by Stokes' theorem, that will give us the same thing as computing the circulation around the boundary. So I'll explain that in an image in just a moment. Before we go too much further, let's just confirm that the answer isn't going to be 0 in this problem, which it is often for these vector calculus questions. So let's just double check that our function f, our vector field, our vector field is this, and if I were to call this first component function f, this second one g, this third one h, if I were to compute f's of y, I get 1, and its comparable function that we should be comparing it to would be g sub x, the partial derivative of this function with respect to x, I get 0. So the vector field f is not conservative, which means that it is not irrotational, so that the curl is not going to come out to be everywhere 0, and so this isn't going to evaluate to be 0 either in flux form by looking at the rotation or by looking at the circulation. If it were conservative, then that closed loop integral would be 0 by the fundamental theorem of line integrals. So we just checked that, and you should always check those in these problems before you go too far along, because it might be a big time saver. So the next thing I'd like to do is let's do a quick sketch of our region. And so what we're told is that we've got the intersection of a plane and a cylinder. So you don't have to draw the picture here, but I'm going to. I think it's helpful that we've got the intersection of a plane and a cylinder. So there's the cylinder, and then the plane, I don't know, maybe passes through these points here. And so let's just try to kind of roughly sketch that plane, imagining it passing through those points, all of those points. And so if we were to look at that intersection, what do we end up with? Well, we would end up with an ellipse that would be their intersection. Okay? So this region here is what we're calling our surface, that shaded region there, and the boundary of that surface in green here, that is our curve C. And we're told that we're going to look down on top of this thing. So if you were to look down on top of this, we're going to orient it so that it is counterclockwise. And so there would be our orientation arrows, which we would need for if we were going to explicitly compute the circulation. So because of this, I think that we should go ahead and parameterize our surface using cylindrical coordinates. So we're going to parameterize S by the function r of uv is equal to, and then our x coordinate would just be u cosine v, our y coordinate would be u sine v, and then our z coordinate in cylindrical coordinates would just be z. But if I were to solve that plane for z, we have that z is equal to 5 minus xy, and so we'd have that the third component for this parameterization is 5 minus u cosine v minus u sine v. And this is for 0 less than or equal to v less than or equal to 2 pi, and 0 less than or equal to less than or equal to u less than or equal to 1. So the next thing we need to do is we need to get ready to evaluate this surface integral here, specifically this flux integral over this surface. But to do so, we're going to have to do two different computations. The first thing we're going to have to compute is the curl at every single point. And then the second thing we'll need to do is we'll need to determine what the normal vector is for this surface based upon our parameterization at every single point. So let's tackle calculating the curl of the vector field first, and that'll be the easier calculation. So to calculate the curl, remember that del cross f is just shortcut notation for the curl of f, but we like to write it this way because it reminds us how to compute the curl. So what we would do is we would take the cross product of I, j, and k of the del operator vector, so that's partial x, partial y, partial z, and then the component functions of our vector value function. And here we'll go ahead and leave it, I think this will work out nicely if we go ahead and leave it in the xyz description. So there's y, the first coordinate function, z, the second, and x, the third. So I'll go ahead and compute this cross product now. So in computing this cross product, I found that the curl everywhere is the vector -1, -1, -1, which is convenient. It'll be easier to integrate. If these still had x's, y's, and z's, just as a reminder, what I would have to do is then convert them based on my parameterization of the surface into the variables u and v. But since each one of these components of the curl is just a constant, there's nothing to convert. So the next thing we need to compute is how we're going to actually dot that with the normal vector of our surface based on our parameterization. So remember, for that, we're going to use the statement, and I want to do this, I think, in blue here. We're going to use the statement partial r, partial u, crossed with partial r, partial v. And this is where this is going to get a little bit messy. So if I first compute partial r, partial u, what I'm going to get, based on my parameterization here, is the cosine of v, the sine of v, and then minus the cosine of v minus the sine of v, where I took the partial derivative of each of those components of r with respect to u. When we go to compute partial r, partial v, this is where you can see this getting messier. This is going to be minus u sine v. This will be u cos v. And then here we've got a couple of derivatives. So this will be, for different terms, this will be u sine v minus u cos v. Okay. So the next step is to go ahead and compute their cross product. So we'll do partial r, partial u crossed with partial r, partial v. Remember, folks, as far as orientation goes, this is where the orientation comes into play. I'm crossing partial u with partial r, partial v. That's related to our choice of orientation here. So doing this cross product is rather tedious. I'll just go ahead and compute it, and then you can check my work. So I went ahead and computed that cross product, and what's nice about this is that, for instance, here we've got a u sine squared and a u cos squared. And that simplifies to just being u. and then these two components end up adding out. Likewise here, this component cancels with this component. These give me a minus u, but remember the minus sign from the cross product for the j hat component gives us a positive u, and this also simplifies to u. So this was probably the most challenging part of the problem, is computing and keeping track of all the terms of this cross product. So double check me on that. But this actually works out pretty nicely. What this means then is that our original line integral, which we said is the same thing as evaluating a surface integral, specifically a flux surface integral, we can now evaluate, based on this parameterization of it, as the double integral over R of the curl, which is this computation here, dotted with the normal vector everywhere to this surface, which is just u dA. Computing that dot product and also putting in the bounds of our parameterization gives us the integral from 0 to 2 pi, 0 to 1, minus 3u du dv. Notice that when we integrate with respect to u, we won't introduce any v's, and so when we do integrate finally with respect to v, it'll just be the length of that interval. So I'll go ahead and pull out that constant as well as the length of that interval. So that comes out to be minus 3 times 2 pi times the integral from 0 to 1 of u du. This gives us minus 6 pi times 1/2 u squared, evaluated from 0 to 1, or we end up with the answer of minus 3 pi. Folks, take a look at this. Let me know if you have any questions. Just as a reminder, the key part was to say, okay, we want to rewrite this circulation integral around the boundary of this curve. That was this green boundary of this ellipse here in 3 space. Rather than computing that circulation integral, everywhere we computed the flux through the surface that's enclosed by that curve. So we had to compute the curl of our vector field, and then we had to compute the normal vector of the surface. To do that, we had to come up with the parameterization of the surface and then compute the normal vector through that computation there. Once we did that, we were able to rewrite this surface integral, this flux surface integral, in terms of the parameterization, and then it was a simple computation. Folks, these problems are challenging. Take a look at them. Let me know if you have any questions, and I'll be happy to help.